Okay, a little guitar introduction to the Calculus Test 3 review with a little slide guitar going on there. Alright, so we're going to do a few related rates problems to begin with, and the things that we did in section 3.11. Now, generally on related rates, just because of the computational tendencies of this, I do allow this on the calculator part of the test. Alright, so one of the other things I do on related rates is I guide you through the problem in a sense, so I have you fill out these parts here. So to begin with, this problem says the edges of a cube increase at a rate of 2 centimeters per second. It's important when you see that rate, then immediately you're thinking, hey, I was given a derivative, okay? Question is, how fast is the volume changing, which is telling you that you're going to find a derivative. Okay, a rate of change when the length of each edge is 60. Okay, so to begin with, it's always good to draw some sort of a picture on this. And what's going on this problem is you have a cube. So I'm going to go ahead just over at the side here and draw out a cube to the best of my ability here. And that'll give us a good idea, hopefully, of what's going on in the problem. Okay. All right, so here is my cube. I'm going to connect these and just kind of label the parts of the cube. Now remember, a cube, all of the sides are equal. So what I'm going to do on this for variables is I'm going to say, well, that part, the length is x, the width is x, and the height is x. Okay, so or base times height, length times width times height. The other thing that's kind of important in this problem is to understand the volume of a cube, because this is talking about a volume, is length times width times height is the general formula, okay? So we need to find a general equation that relates the variables. Now we're talking about volume, so what we'd end up having is just V for volume, and if all the sides are x, length times width times height is just going to give x to the third, so that would be the equation that would relate the volume to the length of the edges. So what particular information is given? Well, they did clearly give you this rate. Now this says the edges increase. Okay, that's talking about a derivative of x. The edge is x. So that means we'd have a derivative of x with respect to time. Y time, well, it's got centimeters per second in it. So that's a given as 2 centimeters per second. The other thing they give you is the edges are 50 centimeters. So we're going to write down also that x is equal to 50 centimeters. That's what we got. Now, what are we finding? Well, read the question. It says, how fast is the volume changing? Okay, so that would be a rate of change. That would be the derivative of the volume, or rate of change of the volume with respect to time. So that's ultimately what we want to find. Okay, those are really, really key parts of the problem right there. And now the rest of it is calculus, and you got to do this, everything exactly right on this. So we're going to write this down, and we're going to differentiate our general formula with respect to t. So we're going to do the derivative of both sides. So I'm going to write how I represent that then. So I'm going to do the derivative with respect to time of the volume equals the derivative of respect to time with x to the third, and you're doing implicit differentiation. So if we do the derivative of volume with respect to time, all we can do is just write that as dv dt. If we do the derivative of x to the third, that's 3x to the second, but since those variables don't match, we also have to multiply that by the derivative of x with respect to t, okay? So what we have to do on this is our job is to find dv over dt. So we should just have to plug in the particular information. And what we were given in this problem is we were given x was 50, and we were also given dx dt was given as the rate 2 centimeters per second. So what we should have to do now is just plug in our general information. We're finding dv over dt. So that is going to be 3 times, and then it's good to put your units in there. X is going to be 50 centimeters squared. We know that. Times dx dt was given as a rate of 2 centimeters per second. So I'm going to go ahead and work this out. So that's going to be 3 times. That's going to be 2,500 square centimeters. And then times 2 centimeters per second. I like to put the units in because this will help you make sense of the problem. So if I just take, and you could use your calculator on this just because, you know, the arithmetic can get a little heavy on these. This is not too bad, though. So 3 times 2,500, times 2 is going to give an answer of 15,000. I think I've got that right. Yeah, I got 25. Oh, you know what? I didn't do this right. It didn't sound right to me. If I do 50 squared, that's 2,500, so I guess I'm okay. So that makes sense. So I've got 15,000. And then notice the units go centimeters cubed per second. And that is a volume, okay? So we were trying to find how the volume was changing over a unit of time, so we end up having that rate. All right, so we have the volume is increasing as the length of the edges continue to increase. So the edges are increasing. Therefore, the rate of the volume is going to increase, so we get a positive value like that, okay? All right, so that's how that would be put together. That's a real basic related rates problem. And what again, I guide you through this, you know, as we're learning this, all right? The next problem, number 2, and, you know, one thing we learned is volume problems. We also learned something that had something to do with Pythagorean Theorem, and we're going to be looking at ones that are fairly straightforward, man. Okay, so this one says a 13-foot ladder is leaning against a vertical wall. A person begins pulling the foot of the ladder away from the wall at a rate. So we got that piece, and we do have a rate. Okay, the question is how fast is the top of the ladder? So we are finding a rate. Okay, when the ladder is 5 feet from the wall. Okay, so the first thing to do is draw a picture. I don't really have room in this blank, so I'm going to go ahead. And I'm just going to draw a picture on this. Okay, so let's go ahead and let's say this is the wall. Okay, so that we're going to start with that. And then we're going to draw the ladder on here. I'll try to kind of color code these things somewhat. Okay, so we have a ladder that's 13 feet, and it's at the, I guess, the top of the wall. Kind of like that. So that is your ladder. And the length of that ladder was given as 13 feet. And then we're going to assume that that's at a right angle like that. Now we have to express this in terms of variables on this. And we really have 2 unknowns on this. The first thing is we can call this x, or we can call it a distance if we want to. It doesn't make any difference. I'm just going to call that d for a distance from the wall. Then I'm going to call this h, the height of the wall. What's happening is the ladder is moving. So the ladder, what ends up happening is the height gets smaller. This person is moving that base like that. So that angle is getting smaller also. So the ladder is going to continue to change over time, and eventually we'd have a ladder that would be flat on the ground, right? Okay, so that would be the situation we have with the picture, okay? Now, as far as this goes, we're going to relate the variables. So these relate by the Pythagorean Theorem. So it would be d squared plus h squared. Those are the legs of the triangle is equal to 13 squared. So we can work that out, and what you would have is d squared plus h squared is equal to 169 if you square that. So that takes care of our general equation then that we're going to differentiate implicitly. Okay, now what were we given? Well, okay, yeah, we have a 13-foot ladder, but that's already built into our equation there we did have a rate of how he's pulling against the foot of the wall. So that distance, that's what's changing at 0.5 feet per second. So we would say the derivative, I'm tempted to change that just because of the Leibniz notation. Why don't we go back and call this, I hate to do this and mess this up, but I think it's better if we just give that something generic like, let's just use x, and then we'd have that. So what we're doing is the derivative of x, with respect to time, that's given as 0.5 feet per second. So see, that's how x is changing. Okay, and what's happening is that's going this direction. So I'm going to say, I'm going to call that negative because we're going against that like that. Okay, so that's kind of at a rate like that. I'm going to go ahead and use that as a negative. The other thing we have is we're going to look at another rate when x is equal to 5 foot. So you're also given that x is equal to 5 feet. So you have this piece of information, then you have that rate. You're generally always given some sort of a rate, and you're trying to find a rate. All right, so what do you want to know? Well, read the question. How fast is the top of the ladder changing? So the top of the ladder is changing by this value of h. Okay, that thing is going downward like that. So what we want to find is we want to find the derivative of h with respect to time, like that. Okay, so we got what we need to know. We got what we're given. Now we're ready to differentiate implicitly. So we're going to differentiate this equation, x squared plus h squared, with respect to time. So we have to be careful about our implicit differentiation. Remember, we have to have, this has to be in your problem, and that has to be in there. When you implicitly differentiate, those two things are going to pop up. So when we do this, the derivative of x squared is 2x. However, the variables don't match, so we have to multiply that by dx over dt by the chain rule. Then we differentiate x squared, which is 2h. And again, the variables don't match up, so we have dh over dt. And then this is a derivative of a constant, so that's going to be 0. Okay? So now what I'm going to do is I got to find, according to this problem, I got to find dh dt. So I need to solve this equation for dh over dt. So I can do a lot of this just in my head. I'm going to say 2h times dh dt is equal to, and I'm going to move this whole thing to the other side, so it's negative 2x dx dt. Okay, then I need to divide both sides by 2h. So I can just kind of squeeze that in like that. So what I have then is dh over dt, which is what I'm trying to find. I'm trying to find the rate at which the ladder is changing as you pull out the base like that. The 2's cross out. That's going to leave negative x over h times dx dt. Okay, now in this particular problem, well, you're given this. You were given that x was 5 feet. Okay, so that is going to plug in there. You were also given that dx over dt was this, so you're going to plug that in, but h you also can find. So if you look at the Pythagorean Theorem, this was 5, this is 13, and this is a Pythagorean triple, that's 12. If you don't know that's 12, then you could go x squared plus h squared equals 13 squared. X is given as 5, and you can use the Pythagorean Theorem to work this out. So that's 25 plus h squared equals 169. So that is h squared equals 169 minus 25, which is 144. And then you can square root both sides to get h is equal to 12. Okay, so this thing right here is also going to be given. So now we plug everything in to get our answer. So x was given as 5 in the problem. I'm going to put my units in there, 5 feet. H, we figured out to be 12 feet. Okay, dx over dt is given as negative, and let's go ahead and write that as negative 1/2 feet per second. You don't have to do that, but I'm going to go ahead and just get a fraction answer. So then what I'd end up having, and what I'm doing is plugging in the particular information here, so I end up with dh over dt is equal to 5 feet times 12 feet times negative 1/2 feet per second. Okay, so what will happen is those cross out, multiply that out, you're going to have negative 5 like this. And I think I also have a negative rate on this, so I do have a negative there I'm kind of forgetting about. So I've got a negative there, so I have negative 5 over 12 times negative 1/2. And then that's feet per second. So that would end up giving you a final answer of 5 over 24 feet per second. And the fact that that's positive just, really came from the fact that I decided to define this way as negative, like this. All right, and that doesn't really make that much difference. On the problem, I defined that rate to be negative. This one turned out to be positive, like that. Okay? All right, so that would be the solution to that problem. And that would be another example of related rates. So related rates are pretty challenging, but the way I do this is I guide you through the problem. And you'll be able to use your calculator for simple calculations because you might need a calculator on these problems some. Okay, next thing is, this would be something you would do without a calculator. This is just section 4.1, diagrams. Can you identify things on this? So an absolute maximum would have to be a point where the function reaches its absolute highest value of y. So there's actually two absolute maximums. And typically what you can do, you can write points. You can also write y values. So I'm just going to write points on this, but 16 is clearly the highest y value that we hit. That's the absolute maximum. And those occur at these 2 points. We'd have a point negative 216, and this would occur at a point 216. Okay, so I'm just going to write those as points, like that. Sometimes we say 16 at x equals negative 2 and x equals 2. You can write it that way too. Absolute minimum is going to be the lowest value of y that we ever hit. So this one, if I approximate that, looks like it's halfway between those two. So that looks like negative 10. So it looks like that absolute minimum is going to happen at negative 10. That's the value of the minimum. And that occurs with the x value of 3. And then I can write that as a point if I want to, 3, negative 10. Doesn't really matter which way you write that. Typically, we write minimums and maximums by their y value, and then we state what x value creates that. Okay, now a local minimum is got to be, when you're doing a local minimum, the key thing is this is what's happening. You have a definite point. You have to have a definite point and a definite continuity there. So you have to be decreasing, and then the function has to be increasing. So it changes direction. So this happens only in one place, really. Okay, you're decreasing here. Okay, so as you're you're decreasing and then you're increasing. So this point right here is going to be a local minimum. So we're just going to put that as the point 0, 0. Okay, this point is not a local minimum because it's an endpoint. So it's got to decrease, then increase. Since it's an endpoint, it's not going to change directions and increase. So that's the only local minimum. What a local maximum is, this just means a small region, a point on the graph, where the graph does this. To the left of it, the function's increasing. Then to the right of it, you're decreasing. So you have to have something going on to the left and something going on to the right. So what you'd end up having on this is you would have, this would be a local max, and that would be a local max right there. The function increases, then decreases. Increases, then decreases. And that's a definite point. So since it's a definite point, that's going to be a local maximum. It's defined at that point. So we can just write this as the point negative 216 and the point 216 like that. Okay, next problem, just kind of checking you on the bubble thing here. So first of all, absolute max on this one, you do not have one. And the reason is because this point is undefined here. So you're getting close to 4, but you're never technically reaching that value of 4. Even though the function's defined, it's not defined on a maximum value. Clearly, this y value of this point is smaller than these here, so you don't have one because of that bubble. The absolute minimum is going to have to be this point right here. Okay, that is a definite point. That's a definite low point. That's the lowest value that y ever hits. So we could say, we could either write this as 1 at x equals 0, has that minimum of 1, or you could just write it as the point 0, 1. It doesn't matter. Okay, now a local minimum, we don't have one. And the reason is because remember, a minimum has to look like this. The function has to decrease, and then it has to change directions and increase. So this is, although it's an absolute minimum, it's not a local minimum because there's nothing to the left of that. That's an endpoint. Okay? This is also not a local minimum because it decreases to the left, but then there's nothing going on to the right. And for the same reason, this is not really a point on there, so you don't really have a local maximum because you can't pinpoint that down to an exact value like this. Although you are increasing, then you are decreasing. That point is defined, but it's not defined at the point that would cause that function to be continuous. You're discontinuous at that point, so you're not going to have a local maximum like that. So that one's a little bit trickier. Okay, next problem is finding absolute extrema on this. Now, typically on this is I also typically will let you use a calculator on this. So you can do this. This would be on a calculator part of the exam. Even though you can do this graphically, you have to follow the directions on this before I'll give you any credit. So the thing on this is we want to find the critical points on this interval. So critical points occur where f prime of x is either equal to 0 or it's undefined. So we're going to start by doing the derivative. F prime of x, and this is a polynomial, so it's a pretty simple derivative. That's going to be 6x to the second minus 30x, and then plus 24. So we're going to set that equal to 0. Now that is always defined. That's a quadratic, so it's continuous. It's always defined. So what I need to do is take this quadratic function, set it to 0, and solve the equation. So even though you can use your calculator for the arithmetic and even to check your answer, which I totally encourage, you still got to show these steps. So the thing to do on this one is, instead of immediately going to factor, hey, everything divides by 6, so you want to go ahead and do that. So you're going to have x squared minus 5x plus 4 is equal to 0. Okay, so now if I factor that, I'm going to have x and x. 4 times 1 is going to give 4, and then I have to have 2 minuses, so the inner and outer will add up to negative 5x. So that's going to tell us that the critical points are going to occur at where x minus 4 is 0. So that's x equals 4. That would be one of your critical points. And then x minus 1 equals 0. You would have a critical point at x equals 1. And you're just given the values on that, okay? The x values is what I'm looking for on that. Now we're going to find the absolute extrema. Now you have to show this. Also, you want to notice that I've given you an interval, and these critical values have to be in the interval. So since 4 and 1 are within that interval, then they are possible absolute extrema. So then what I'd want to do is I'd want to see that you do this. You can use your calculator to assist you a little bit with this. But you're going to do, first of all, you're going to do the endpoints. You're going to do f of 0, and then you're going to do f of 5. Okay, you can use your calculator to assist you with this. So I'm going to go 2 times 0 to the third minus 15 times 0 to the second plus 24 times 0. Okay, and that works out to be 0. Okay, so that actually gives you a point, 0, 0. And I'm going to kind of highlight these points as we do these. Now I'm going to go to f of 5. So I'm going to go up to the function I gave you and evaluate that at 5. So I'm going to do 2 times 5 to the third minus 15 times 5 to the second plus 24 times 5. And again, I'm allowing you to use your calculator on this. I don't want you to spend a lot of time doing tedious calculations, although this is not too hard to do without a calculator. We can just go 2 times 5 to the third and do this in one step, minus 15 times 5 to the second, and then plus 24 times 5, and get that to calculate as negative 5. So that means you have another point. X is 5, y is negative 5. Okay, so those are the endpoints. You've got to work with the endpoints. Now you've got to work with the critical points. So these two things right here are your endpoints. It is possible that your endpoints can be absolute extrema. Now take your two critical points, which are 1 and 4. So we're going to do f of 1, and then we're going to do f of 4. These are the critical points. And again, we can use our calculator to assist us a little bit with this. So we've got 2, just plug in your value of your critical point, x equals 1. So we're going to do 2 times 1 to the third minus 15 times 1 to the second plus 24 times 1. And I'm going to go ahead and just kind of speed up and calculate that. So I've got 2, and you can put it in exactly like this. 2 times 1 to the third minus 15, and you can do whatever you want to in your head, by the way. This is not very hard to do. Okay, and then plus 24 times 1. So you could actually do this one in your head. So that's going to give 11. So that ends up giving a point, 111. So I'm going to write that point down, and then I'm going to highlight that as another possibility. Okay, now I need to do f of 4. So when I do f of 4, I'm going to go to the function, the original function, and plug in 4. Don't plug in the derivative, plug into the function. So you're doing 2 times 4 to the third minus 15 times 4 to the second plus 24 times 4, like that. So evaluate that function. So let me pull out the calculator, and then we'll do this. So let's put it in like this. 2 times 4 to the third minus 15 times 4 to the second plus 24 times 4. I think I got an extra parenthesis there that I don't need. So we got that. That gives negative 16. So that's going to give a value. X is 4. Y is negative 16. Now what we do on this is we've got our critical points here, and we've got our endpoints here. So the idea is we just need to put these in order. These are your critical points. These are your endpoints. Okay, which one has the biggest y value? That's the biggest y value. So that means this is going to be your absolute max. So we say we have an absolute max at the point 111. Which one has the smallest y value? This does. Okay, so that would be your absolute minimum. Okay, so we're just going to write that in as the point 4, negative 16. Now, I would want to see all this work on your problem to get credit. Although I'm letting you use a calculator to assist you with arithmetic, what I'm wanting you to do is probably check your answer, and I'd certainly encourage this, so it doesn't take very long to do that. So I'm just going to put the function in, which is 2x to the third minus 15 x to the second plus 24x. And then we're going to graph this. We're also going to pay attention to the interval. Remember, the interval is 0 to 5. So when we do our window, we just got to go 0 to 5. And for the window, see, our max was 11, our min was negative 16. So I'm going to make this y value go to negative 20, and then maybe make the max go to 20. Like that, maybe scale by 5 or something. Okay, so now if I graph this, this should verify everything and make sure you're right. So I'm wanting you to use your calculator to verify this. Sometimes they even have you graph this. So if you want to verify this, the absolute min, all you'd have to do is just trace at 4. So if you type trace and put 4 in, you can tell that's blinking at the minimum, so that's right. And then if you want to trace at 1, type trace 1, that's blinking at the max, and see that value is coming up as 11. So you can use your calculator to check, but you have to show all these steps. You have to find your critical points. You got to show that you're evaluating endpoints and critical points. If you don't do that, you aren't going to get credit. So I'm just simply using your calculator to assist with arithmetic and also to check and verify, because I do like you all to be able to check and verify with technology on some of these. Okay, now moving to the next one. This is just a basic graph where I'm giving you information to fill out. Okay, so first of all, let's just kind of go through this and look at increasing and decreasing. So I'm going to just sort of trace through the graph. So if we start here, the y values are clearly getting smaller. And then we get to this point right here, the derivative is going to be 0. Okay, but then what's going to happen is it's just going to continue to decrease. So that's going to decrease, and then you've got another point where you have a level tangent line, so f prime of x is equal to 0. So what you're doing is you're decreasing. You got to break it up into these intervals like this. So you're going to say negative infinity until you get to this point right here. You got to exclude that point because the derivative is 0. Remember the definition of increasing. Hold on, I'm putting this in the wrong answer blank. We're looking at decreasing right now. So decreasing is a place where the first derivative is negative. Okay, not where it's equal to 0, but where it's negative. So you have to break this up into two intervals. So you're going to have to say negative infinity to 0, union, then 0 to 3. Okay, like there. So you got to look at that value, you got to look at that value. You got to break it up into two intervals. Okay. Now I'm going to change colors here, and let's go trace this part out then. Okay, so the rest of the function, the derivatives are positive. So remember what you're looking for on increasing is a place where the first derivative is positive. So that's going to be from 0 to infinity. All of those tangent lines have positive slopes. So that's going to be on the interval 3 to infinity. Remember, you always name these with x values. Use x values for your intervals. You always do. Okay, so that'll take care of that. So I'm going to erase that. Now, the other thing is, while we're at it, we can go ahead and answer this. F prime of x is equal to 0 at two places. It's at x equals 0 and at x equals 3. So those are the two places where your tangent lines, the slope of your tangent lines, are horizontal. So clearly you would have a horizontal tangent line there, and also clearly you would have a horizontal tangent line there, like that. So that explains that. Okay, now I'm going to erase this stuff I did on the graph and just kind of start over again, because now we can begin to look at the concavity. And when I look at the concavity, the thing that you want to kind of remember is this. Okay, concave up can look like this, it can look like this, or it can even look like this. So it's kind of a smiley face or a half of a smiley face. Concave down can look like this. It's like this. It could be something like this, half of your frown, like that. Okay, and then points of inflection are going to be places where the concavity changes. So clearly if you kind of go through and look at this, I'm going to label this just with different colors on this. Right now, you're concave up in that area right there. So you can see that you kind of have that piece right there. Then the concavity is going to change. So let's go to this color right here. So you've kind of got that. So you've got this little piece right there that's concave down. Then it's going to change directions again to being concave up, and it'll be concave up the rest of the way. So the rest of the way, you've got that shape like this. So you've got places where the concavity changes, and then these things here are going to be the inflection points. Okay, so we're going to say that we're concave up two places. Negative infinity, this is what I highlighted in orange, to 0. Okay, then it's going to be from 2, and then from then on out. So it's going to be 2 to infinity, like that. Concave down is going to be this little slice here that's in green from 0 to 2. And then your inflection points, now you're supposed to give points, so you should be able to identify what these points are on this graph. So one of those points is 0, 0. And then this point right here looks like 2, negative 16. So I made the graph, so it's pretty clear what the points are. So we would have inflection points at 0, 0, the concavity changes at that point, and also at 2, negative 16. So you have two inflection points like that. Okay, one thing that kind of helps on this too is what happens at this point right here. If you have an inflection point, I'll try to draw this on here the best I can. I'll just use something like red and kind of show you what happens. So basically on an inflection point, like this point right here, the tangent line, part of the tangent line is above the curve, and then the tangent line becomes below the curve. So it's just kind of slicing right through there like this. At this other point of inflection, you actually have a horizontal tangent line like that. So again, what's happening is you're below the curve here and above the curve there. So that's where your inflection points are. And on a problem like this, I try to make it pretty easy to interpret where there's no guesswork on that. Okay, so I'm going to erase this, and then we'll just finish the problem up with talking about the increasing and the minimum, the minimums and the maximums like that. Okay, so one thing is clearly this point right here is a local minimum. And remember, a local minimum, you have to be doing this. Okay, the function has to change from doing this. It's got to be decreasing to the left of it. Then it's got to change directions. And then it's got to start increasing. So it's decreasing, then increasing. So that's clearly going to be a local min. And that's the point 3, negative 27. So that is a local minimum. Now that is also the absolute minimum. That is the lowest value of y that this graph ever hits. Okay, now we're going to see if we have a local maximum. Okay, there are no places. Remember, a local maximum is going to be a place where the graph has to increase, hit a definite defined point, got to be continuous there, and then it's got to decrease like this. Okay, so that's what a local maximum is. Okay. All right, so this one does not have one. All right, so that would be what you're looking for in that problem. This is just kind of knowledge level stuff. Can you take a graph and determine all these parts of this then? Okay. Next thing will be something I allowed you to use your calculator on, but you do have to follow directions on this or I won't give you credit. And the only reason I'm letting you use a calculator on this is so that you can verify. I do want you to be able to verify with technology and just help yourself a little bit with arithmetic. So what I've done on this is I've given a function. You're going to use the first derivative test to identify where it's increasing, decreasing, and you're going to find local minimums and local maximums on this then, okay? So the first thing we want to do is we want to find the first derivative. This is a polynomial, so we're going to have 10x to the fourth minus 20x to the third minus 30x to the second, and of course the constant is plus 0. So we have that. So we got to find our critical points first of all. So let's find the critical points. We find the critical points by looking where the derivative is 0 or undefined. This is defined everywhere. So we're going to take this first derivative and we're going to set this equal to 0. And we're going to solve that equation. Okay, now you're going to solve this by factoring, but notice that you can divide by the common factor of 10. You can divide by constants, but don't divide by variables. That'll mess the whole thing up. So this is going to give x to the fourth minus 2x to the third minus 3x squared is equal to 0. Now we're ready to go about factoring this then. So you notice that this has a common factor of x. You're going to work with the lowest exponent like you've done in algebra. So you want to take an x squared out. That'll leave you x squared minus 2x minus 3. If you factor something on an exam, gosh, check it. X squared times x squared, x squared times x, and so forth. Distribute it out and make sure. Now you do have this trinomial, I think, also factors. Typically I'm looking at things that factor just to speed up the time process on this. So we've got x and x, 3 and 1 to get negative 3 with a negative and plus. So notice you've got negative 3 and positive 1 adds to negative 2. So what we're going to do to find our critical points then is we set x equals 0, we set x minus 3 equals 0, and then we set x plus 1 equals 0 like this. Okay, so this is going to be x equals 0. You can do that in your head. This is x equals 3, and this is x equals negative 1. So those are the critical points. So that'll take care of the first part of the problem then. Okay, so now we got to go to a sign chart. So if I'm asking you to do the first derivative test, you got to do a sign chart. If you don't do a sign chart, you don't get any credit for the problem, period. You can check on your calculator when you're done, and you can use your calculator for to check things. But the point of this is do you know what I mean by the first derivative test? Okay, so what we're going to go ahead and do is we're going to go ahead and let's make a number line. And go ahead and make our sign chart out like this. So we got this. And our derivative is equal to 0 at these places right here. So we're going to just go through and look at -1, 0, and 3. These are all places where f prime of x is equal to 0. Okay, so we got that, and then we're just going to analyze the derivative. The best way to analyze this derivative is to analyze the factored form. So we're going to look at this, and then you can use your calculator if you need to, but this is a problem that's designed so calculator, you don't really need it too much on the problem. So we're going to look at x squared times x minus 3 times x plus 1. And we're going to use test points on this. Okay, so I'm going to go ahead, and let's start here. Let's use a test point of -2, something that's less than -1. So if you plug that in, now the thing on this is, if you plug a number into x squared, you're going to get a positive. So we can go ahead immediately and just put positive there. Okay? And then let's just kind of do this in our head. If I plug in -2 there, I get a negative. If I plug in -2 here, I also get a negative. So positive times negative is positive, is what the derivative is. Okay? Now let's move on and do another test point. So you don't really need a calculator on this problem, although I let you on some of these. Okay, this one probably is not bad to do without a calculator, though, actually. Okay, so let's see. With this one, let's use a test point of, say, -1/2. Now remember, if you plug -1/2 in, square it, you're going to get a positive. Okay, if you plug -1/2 in there, you're going to get a negative. If you plug in -1/2 here, -1/2 plus 1 is positive, so you end up getting a negative result right there when you multiply those three things out then. Okay, now move on to here. Let's use 1 as our test point. Okay, so I'm just going to start over again and see if I can evaluate this at 1. 1 squared is positive. 1 minus 3 is negative. 1 plus 1 is positive. So on this one, you're going to have a positive times a negative times a positive is going to be a negative. Okay, like that. Okay, test point bigger than 3. Let's work with 4. Okay, go up here and use 4. So 4 squared is positive. 4 minus 3 is positive. And 4 plus 1 is positive. So you've got a positive result right there. So according to what we have then, is we're going to be increasing on these places. We'll be increasing wherever the derivative is, first derivative is positive. Okay, then we'll be decreasing wherever we're negative. So we're going to be decreasing here, and we're going to be decreasing here. Okay, like that. Okay? All right, so let's go ahead and write this interval on here. So we're increasing from, and I'm going to just sort of highlight this, we're increasing like this. Remember, these things are open intervals, so we're going to write this as increasing on the interval -infinity to -1, union, and then picking up at 3 to infinity. Okay, decreasing is going to be in these two places. Now you do have at 0, the derivative is 0, so you got to exclude that and break this down into two intervals. So you're going to write this from -1 to 0, union, then from 0 to 3. So you're doing that. Now, what you'd want to do on this, and now that I think of this, this is the kind of problem I made a mistake on this. I don't want a calculator on this problem. I want it on certain problems, but not this one. Okay, so now what we want to do is, I think the next problem that I'm going to do is one you can use your calculator on. Okay, so with this one, what we want to do here is just kind of draw a picture. Okay, what I'm going to do is I usually just sort of take like a marker or something and just try to think about what my problem's doing. Well, one thing it's doing is it's increasing of some sort. Then it's going to be decreasing. But what it's going to do is it's probably going to do something like that. You know, if you just kind of think through the logic of the graph, it's going to hit a high point. That's not going to be a max or min. That's just going to be a place where the derivative is 0, and you got that. So you're going to have horizontal tangent lines actually in 3 places. That's what we found with the critical points. So then what we're going to have is you're going to have a maximum here, just one local maximum. So that local maximum is going to be at x equals, I just want you to put the x value here, x equals -1. Then it has a local minimum at this point, x equals 3. Okay, since you're not going to use a calculator, you don't have to worry about anything on that as far as finding the y values like that. Okay, all right, so that's no calculator on that. Sorry about that. I think the next one's a little bit better example. Okay, so yeah, this one I intended for you to be able to use your calculator on, not the last one. Okay, I always like to look at one problem that's simple in the context that it's polynomials, everything factors, arithmetic, very simple. Okay, I make it up that way so that you don't need your calculator. Okay, now this one we're going to analyze the concavity. Okay, so with this one, remember concavity, the visual that you can remember is if the second derivative, that's the tattoo, is positive, then you're concave up. Okay, if the second derivative is negative, then you're concave down. Don't forget that tattoo on the cheek of the dude. So we're going to go ahead and take 2 derivatives. So the first derivative, f prime of x, we're going to have to use a product rule on this. So we're going to do the first times the derivative of the second plus the second. This is a fairly simple derivative times the derivative of the first. Okay, so when we do that, we're going to have e to the x times 1 plus x minus 3 times e to the x. Okay, so that's your derivative. And then you probably want to go ahead and put this in a factored form. Now, ultimately on this one, you got to find the second derivative though. But I'm going to go ahead and factor it because it might make the second derivative a little bit easier. Okay, so let's do that. So let's take e to the x out. You're going to be left with 1 plus x minus 3. So that's how the factoring goes. So that is going to be e to the x. So you can put together 1 minus 3 and then you get x minus 2 like that. So that's your first derivative. Now you want to go to the second derivative, which is very similar. It's a product rule. So you're going to take the first times the derivative of the second. Derivative of the second's 1 plus the second, x minus 2. Derivative of first is e to the x. You're welcome to do that in your head if you want to. And then we can do a factored form on this again, which I recommend. So what you're going to do is take out e to the x. You're going to have e to the x times 1 plus x minus 2. So that's going to be e to the x times x minus 1. Okay, so that is your second derivative. That's what we're going to use to analyze the concavity then. Okay, all right, so that'll take care of the first part of the problem. Okay, so what we're going to do is we're going to find places where this derivative is 0 or undefined. So let's work with the second derivative. F double prime of x is e to the x, x minus 1. Now see, that's already in a factored form. So you could set that to 0, and then you've got 2 factors. You've got e to the x equals 0, you got x minus 1 equals 0. Well, clearly the x equals 1 is going to be a place where the second derivative is 0. This one does not exist. If you take e to the x, any number, just think about this, any number to any power always gives you a positive number. So if you have a positive base and any exponent, that always gives a positive number, so that doesn't have a solution. So what you'll end up doing on this one is you're going to make a sign chart on this. So let's go ahead and put together a sign chart. And this will be a pretty straightforward sign chart. There's only one place where the second derivative is equal to 0, and that's at 1. So we'll go ahead and just do this. That's x equals 1. That's where the second derivative is equal to 0. Then we're going to do test points. Now we're going to plug our test points into the factored form of that derivative. So let's work with these test points. Let's work with 2 here. So if you did e to the second times 2 minus 1, replacing x with 2, you would get a positive number. E to the second's positive. 2 minus 1's positive. So this is going to be positive times positive, so that's positive. that's going to mean that you are concave up. Or the smiley face is what that is. Let's use 0 as our test point below 1. So then we would do e to the 0 times 0 minus 1. E to the 0 is 1, so that's positive. 0 minus 1 is negative, so this is negative. That means you're concave down. All right, so what we'd end up having on this then is we would say concave up would be 1 to infinity. So we'll write that interval. Concave down is going to be less than 1. So we can write that as the interval negative infinity to 1. And then your point of inflection is going to be at 1. Now we can use the calculator to get this then. Actually, you don't really need a calculator much on this problem either, but I'm going to allow you to do that on some of these problems. So with this one, you could plug in 1, and you could get a decimal on your calculator on this. So if you plug in, if x equals 1, and the function is g of x equals e to the x minus 3, so if we just find g of 1, we're going to get e to the first times 1 minus 3. So that's e to the first times negative 2, so that's negative 2e. So the point of inflection is going to be negative 2e. This is another problem that you don't need a calculator on that much. All right, now what you could do on this, if I'm allowing you to use the calculator, which we'll do on some of these problems, then you can put this in. You've shown all the calculus, so you've earned your credit. So it's just basically now you can see if you're right. So the way you would put this in is you would put in second ln to get e to the x to come out, then times x minus 3. And then we could probably just try this in a standard window, zoom 6, and see what we get here. Okay, so we're looking at the concavity. So you see the graph. And if you wanted to trace at your point of inflection, you have a point of inflection at x equals 1. So if you trace at 1, you can tell that looks like the function is concave down, then the rest of the way it's concave up. So you can use your calculator to, excuse me, to assist with the checking aspect of that then. Okay? Okay, so next thing that I'd like to go ahead and run through is a little bit of curve sketching. Okay, so I can get this thing to work in here. Put my calculator away here. Okay, so a little bit of curve sketching. All right, now these kind of problems can be a little bit difficult, but I always like to have one thing on here on a non-calculator part of an exam. Now what we're going to try to do is identify what everything means in here. So I'm going to start with this. If the second derivative is positive, that means that you are concave up. Okay, that's a piece of information on that interval. So we have that. Okay, now we got another piece of information. This time it says the second derivative is less than 0. So that means we're concave down on that interval. So that's pretty simple. Okay. Next thing that this gives is this is given concave up. Since the second derivative is positive, and that's going to be on that. And then finally, this one, you've got the second derivative is negative. So that means you're going to be concave down on that interval like that. So what we're going to do is we're going to go ahead and just try to draw a graph that has these pieces of information on it. So I can ask this problem in all kinds of different ways. This one mainly is doing the concavity. You can also have problems that involve increasing and decreasing. Just kind of checking your knowledge on this. So I'm going to go ahead and look at these key points. -2, something kind of key is going on there. So when I'm doing these problems, I like to just sort of put a dashed line to help me understand this. And then from -2 to 1, the concavity changes. So we've got that. And then it looks like from 1 to 3, you got something kind of important happening at 3, and then 3 to infinity like that. So basically you can draw this in all kinds of different ways on this. One way you could draw this is, okay, well you're concave up in this interval, then concave down. So you could do something kind of like this if you wanted to. You could, you'd have to have some sort of a point of inflection right there. So you could do something like this. Then you're going to be concave down, so you could do something kind of like this, and then you just got to have another point of inflection. Then you'd be concave up again, have another point of inflection and concave down. So that would be one way. There's an infinite number of ways to write that. And then you would have points of inflection, so you want to kind of draw this graph in such a way that it's pretty clear. I mean, it doesn't have to be perfect, but the idea is the tangent line through there shows that inflection point. You're above the curve, you're below the curve. Same thing's kind of happening here. You don't have to put these on your graph. I'm just showing the concept of a point of inflection. And then you would have a point of inflection here, so the tangent lines should slice right through that. So part of it's above the curve, part of it's below the curve like that. Okay, so that would be one possibility. Okay, that's one thing that you want to be able to do. Okay, now let's do the rational function. I'm going to do the recording of this, I think, in two parts so that they're not so long. So I'm going to do this rational function next. This is what we learned in 4.3, so this is kind of the key thing I want you to be able to do on this. Okay, so first of all, we're going to go ahead and let's start by finding our asymptotes and remember how to do that. So I'm going to do some of my work kind of at the side of the paper here. Some of it I'm going to do below here. So if you're going to do a vertical asymptotes always occur where the denominator of the simplified form is 0. Now you got to see if you can simplify this thing first of all. So h of x, yeah, you could factor a 2 out of the top and have 2 times x minus 2 over x plus 4. And nothing cancels out, so all you would have to do to find a vertical asymptote is take the denominator and set that equal to 0, and that would give x equals negative 4. Okay, so that would be your equation of your vertical asymptote is x equals negative 4. Okay, if you want to find a horizontal asymptote, you can use the rules that I taught you. There's more than one way to do this, but one way to look at this is just look at, you have h of x equals 2x minus 4 over x plus 4. Now the degree of the numerator is the highest power of x, which is 1. The degree of the denominator is also 1, so since those are the same, then anytime the degree of the top is equal to the degree of the bottom, then the ratio of these leading coefficients gives you that horizontal asymptote. So that's going to be y equals 2 over 1, or just y equals 2. Okay, if you forget that, you could also do the limit as x goes to infinity of 2x minus 4 over x plus 4. And if you did this is, it's really an infinity over infinity limit, so you could do L'Hopital's rule on this. So if you wanted to go through by L'Hopital's rule and just do the derivative of the numerator and denominator, you would end up having the derivative of the top is 2, derivative of the bottom is 1, so you get 2. You can do it that way if you have to, just in case you forget that. Okay, so we got that. Now let's go ahead and find intercepts while we're at it before we get into the calculus. So we got a horizontal, we have a vertical asymptote. Now let's find a y-intercept. So y-intercepts, you always just set x equal to 0. So we're just going to evaluate the function at 0. So we're going to do 2 times 0 minus 4 over 0 plus 4. So that's negative 4 over 4. So that is negative 1. So your y-intercept would be the point 0, negative 1. Now you're not allowed to use a calculator on this problem. I've made the problem simple enough that you don't need a calculator on it. Okay, so we got our y-intercept. So that's all taken care of as negative 1. Now the x-intercept on a rational function, really just look at the numerator. You can just look at the numerator equals 0. So if you go back to the original, see there was no cancellation. So you don't have to worry about like a hole or anything like that. You just do 2 times x minus 4 equals 0. So that's 2x equals 4. You can divide by 2. So that gives x equals 2. Okay. So you end up with a x-intercept of 2, 0, like that. So that's just kind of the algebra. Now what I'm going to do is to find increasing, I got to work with the first derivative And then to get concavity, of course, we've got to work with the second derivative. So let's go ahead and start by finding the first derivative, which is going to be a quotient rule. So we're going to do the bottom times derivative of top. The derivative of top is 2. You can just do that in your head. Minus the top, 2x minus 4, times the derivative of the bottom, which is 1. And that's all going to be over the bottom squared. I'm not going to do anything with a real lengthy, complicated derivative because there's not time to deal with that much. So now, what I want to do next is finish up that derivative. Hold on just a minute. I got my cords all tangled up here in my home office here. God. I hate cords. Okay. All right, so what I want to do next is let's go ahead and just do the algebraic simplification on that and start with that. Okay, so I'm going to have 2x plus 8 when I do a distributive property there, minus 2x plus 4. Be careful about the sign. You know, if you make any algebra mistake on this, it's going to kind of seriously mess everything up. That'll cancel that out. That will leave the first derivative is 12 over x plus 4 to the second. And we're going to do a sign chart on that. Okay, now I'm going to go ahead and just kind of highlight that as the first derivative, and then we'll deal with that here in a minute. So we've done the quotient rule, and then we did the algebraic simplification on that to get that result. Now let's go ahead and do the second derivative. And when we do the second derivative, we're going to have to use, you actually don't have to use quotient rule on that, although you can if you want to. You can write this as 12 times x plus 4 to the negative 2. That's the way I do the derivative, is just do that. So if I do that, I can bring the 2 down to get negative 24 times x plus 4. Subtract 1 from the exponent to get negative 3. Derivative of inside is 1, so that's going to give negative 24x plus 4 to the negative 3. And then you can write that as negative 24 over x plus 4 to the third power like that. So that's going to be our second derivative in a simplified form. Okay, I'm not going to make anything, real difficult on a rational function just because of the time constraints that are dealing with in a test. So we've got that. Now what we're going to do is we're going to just do 2 sign charts. So to begin with, let's do the first derivative test, and let's do a sign chart for the first derivative. Okay, so let's go ahead and get that put together. So I'm going to draw a number line here, and this is going to be the first derivative test. Now what you want to look at is you want to look at this first derivative. I want to just kind of do a little bit of work over here at the side. And on this first derivative, you have 12 over x plus 4 to the second. You got to find the critical points. If you set that to 0, there's no solution to this equation. But you're undefined. The derivative is undefined at x equals negative 4. So what you're going to have is you've got a place where the derivative does not exist. Okay, so there's no derivative. I'm going to put no derivative there. Okay. So what we're going to do with this then is we're going to use test points, and we're going to plug this in the derivative. And the thing about this is I want you to notice that when you do this thing, the numerator is 12. That's always a positive number. The denominator is something squared, so that's also a positive number. So you're going to end up on this problem with a positive derivative in both places, which is going to tell you that the function's increasing on these intervals. Now what's happening is you have maybe an asymptote there. Remember, we had a vertical asymptote at negative 4 like that. So that's how that sign chart goes on that. Now you can do test points. I mean, if you did like, say 0 there and negative 5 there, trust me, it'd work out to be plus plus. But if you can do something in your head and save time, then by all means you want to do that. Okay, so the next thing I want to do is a sign chart for the concavity. Okay, so the second derivative, when we worked out the second derivative, we have negative 24 over x plus 4 to the third. Again, if you set that to 0, there's no solution of that equation, but you're undefined at -4, so you're going to end up on this having a very similar sign chart. At x equals -4, there's no derivative. Right? Now what we're going to do on this one is the numerator is negative. The denominator will change. So let's do test points. So let's do a test point of, say, 0. So if you plug that into the derivative, you would have -24 over 0 plus 4 to the third. Well, that's a negative over a positive. So that's a negative, so that means you're going to be concave down. Okay, let's take a test point of -5. Okay, if you do that, you're going to have a negative numerator. The denominator is just going to be -5 plus 4 to the third. That's -1 to the third, so that's negative. So you have a negative over a negative is a positive. That means that you're concave up. Now you're ready to use the information in these sign charts then to get the answer. So we're going to be increasing like this. Increasing forever to the left and forever to the right of -4. You'd have to break that up into 2 intervals. So for my final answer on increasing, I'm going to say -infinity to -4 union -4 to infinity. Okay, we're never decreasing, so we can just put never on that. Okay, so the sign chart gives us, keep in mind, you're not using your calculator on this or anything. Okay, so that takes care of that. All right, now we got to look at our concavity. So we're concave up, -infinity to -4. And we were concave down from -4 to infinity. Okay, now we're going to take all this information and then we're going to do a graph. Now I'm going to have to erase a bunch of stuff on this. So I'm going to do that when I do my graph. I can probably actually go through and take this information and maybe just kind of put a graph up here on the side or something like that, because you don't have to do much on your graph. So I'm going to go ahead now and take all this information that I have, and then let's just draw a graph up here, and that'll be good enough. So you can see kind of what I'm doing. Okay, so the other thing I have you do without your calculator, you're not allowed to use a calculator on this, is to sketch your graph. So the best thing to do is to start with all the asymptotes. So you have a vertical asymptote. Let's go ahead and do these 2 asymptotes and start there. So we got a vertical asymptote at x equals -4. So let's just put a dashed line, vertical line that goes through the vertical asymptote like that. We also have a horizontal asymptote at y equals 2. So let's go ahead and let's do a vertical asymptote like that. Okay, so we've got that. Now the rest of it we just sketch in. We just figure out what we have. So our concavity is kind of the key on this to me on this problem. So if I go through and do this then with this, let me pick like let's do purple. Hey, we lost Prince this week, so let's do purple. Let's do a rational function in dedication of Prince. Okay, all right, so concave up from -infinity to -4. So we're going to have a concave up shape going like this. And remember, you have to approach a vertical asymptote either up or down, and you have to level off. So you're going to end up having a part of a graph that looks like that. Okay, then let's put our intercept. So we have a y-intercept at -1. So we're going to go ahead and put that intercept there. We have an x-intercept at 2. So we're going to put that intercept there. So you want to go ahead and get those 2 things on there. Okay, then you can see your concave down. So you're concave down. So let's do the pretty purple rain concave down. Okay, and let's see. I'm getting carried away here. I don't even know what I'm doing. Okay, there we go. So you're going to have to go through those points. You're going to have to level off towards that. And you're going to have to go down towards the asymptote like that. So that would be a rough graph of how that looks. Okay? All right, now I'm going to go ahead and stop this here because I want to do this recording in 2 parts. And I'll do the second part and record that next.